this video is on probability and on the topic of discrete random variables. Today we're learning to know the conditions that define a discrete random variable and to be able to prove whether a model is or isn't a discrete random variable. We'll be creating probability distribution tables from a description, solving problems that involve conditional probability, and also finding the expected value of x, which is written as e of x, the variance of x, var of x, and the standard deviation sd of x. Okay, so discrete random variables are outcomes from experiments that can be counted, and they must have distinct values only. This is the discrete part. So for example, 1, 2, 3, red, blue, green, etc. So they must have fixed, possible, distinct values, so not on a continuum. Now the probability that some variable x takes a particular value x here, so uppercase describes the event that's happening, and lowercase x is the particular value. So for example, roll the dice is x, get a particular value, 1, 2, 3, 4, 5 or 6 is little x, is written as the probability that x equals x. Now this is probably what you used to writing, but we're going to be moving on to this as our most common way of writing the probability of some particular thing happening. Now, if x is the variable associated with the possible outcomes of throwing a dice, we would write the probability that x equals 5 equals 1 over 6. So that's how we're going to be writing them from now on. Now these are two very important conditions that define a discrete random variable. So in order to be a discrete random variable, first we must have countable outcomes that are specific, discrete values, distinct values. The other is that the probabilities for each one must lie between 0 and 1, and the sum of those probabilities must equal 1. So I'm sure you know these things before, you've heard these things before, but this is how we're going to write it now, using this sigma to mean the sum of the probabilities that x is equal to x, so that's all of them is equal to 1. In the case of rolling a dice, you would have a 6th, the 6th, the 6th, the 6th, the 6th, the 6th, and that would equal 1. Okay, so here we have some examples, and job is to work out whether they represent discrete random variables or not. So I've got the example down here of the dice. If you roll a dice, you'll either get a 1, a 2, a 3, a 4, a 5 or a 6, and the probabilities are a 6th, a 6th, a 6th, and so on. Could we do the same for each of these? So number of goals scored at a football match. Well, there would be a countable number of goals, and it would be fixed outcome. So there would either be 0, 1, 2, 3, 4, 5, 6, and so on. So yes, we could for A. Heights of students in a maths methods class, that one's a little trickier. Yes, we could count them, but how would we define our measurements? I think that's the problem. Do we have countable outcomes at 1.75 meters, 1.76 meters, 1.77 meters, and so on? We'd have a very big table. It's usually thought of as continuous data rather than discrete data, because it could be more and more finely chopped up. You could chop a centimeter into millimeters and so on. Shoe sizes, on the other hand, that's discrete data. It has particular values, and we could count the outcomes. So number of people with size 5, 6, 7, 8, 9, 10. So that's a yes. Number of girls in a 5-child family. We could have 0 girls, 1 girl, 2 girls, 3 girls, 4 girls, 5 girls, and we could count them and see how many families had 0, 1, 2, 3, 4, and 5, that sort of thing. So that would work. Time taken to run a distance of 10 kilometers in minutes. Now, I'll put a question mark next to this one, just because given that we've chopped it at minutes, we now have fixed outcomes, but we still would have a lot of them. So for 10 kilometers, you might have anywhere between sort of 20 minutes and an hour, perhaps, and that would be 20, 21, 22, 23, 24, 25, 26, 27, and so on. So we'd have a very big table here. It's not the kind of thing that lends itself to these kinds of probability distribution functions. Time usually is thought of as being continuous as well, although we have restricted it to minutes here. Okay, here's our first question about drawing up a probability distribution table. Let x represent the number of tails obtained in 3 tosses of a coin. Draw a table which displays the values. Now, usually, best way to obtain the probabilities for something like this is going to be a tree diagram. We have a couple of events, we know the probabilities, so if we draw it out, we have our first event, it's either heads or tails, and then we do it again. It's either heads or tails for the second toss, and then the third toss. Heads, tails, head, tails, heads, tails. Now our outcomes then would be head, 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 tail. Next one would be head, tail, head, head, tail, tail, and so on. And the probability of any one of these, because the probabilities are the same, it's a half here, a half here, a half here, so it would be a half times a half times a half. So 1/8 is the probability here, and every single one of these individual ones has a probability of an eighth. Okay, so we want to know, what are we looking at? The number of tails, sorry. So number of tails here could be anywhere from 0, 1, 2, or 3. And then the probability that x equals x, the probability that it's 0. So 0 tails means you must have head, head, head. And that is 1/8. We've already established that. 1 tail would come from this one, and this one. So there are 3 of them, making it 3/8. 2 tails, you can see here, 2 tails there with that tick, 2 tails there, and 2 tails there. So 3/8, and again for 3, just 1/8 there. Now we've drawn up our probability distribution function, and there are 2 things that we should check to make sure that it is a probability distribution function. Remember, the first condition was that the probabilities must all be between 0 and 1. As you can see, these are all between 0 and 1. The other is that they must sum to 1. So if we had 1, 3, 3, and 1/8, we would have a total of 6, 7, 8/8, which is 1. So they do. Our next job is to identify out of these probability distribution tables which ones are discrete probability functions and which are not. So first, just pause the video and see if you can work out which ones are, which ones aren't, and why. Okay, so these are all between 0 and 1, so that's good, and 0.5, 6, 7, 8, 9, 10, so they add to 1, so this one is okay. These are all positive, and 5, 6, 7, 8, 9, 10, they add to 1, so that one's okay. These ones are all positive, don't worry about that being negative, that's just the result, the probability is positive, and we get 2, 3, 6, 9. Now, so there's a problem, this one is not, and this one we have a negative probability, so straight away that one is not either. Now interestingly, I think this one is designed to add up to 1, so 5, 6, 7, 8, 9, 10, 11, 12, yes it adds to 1, but it's not a probability distribution function because it's negative there. So the problem with it is that it fails this test, and the problem with this one is it fails this test, it doesn't sum to 1. Here we have to find the value of k in these discrete probability functions. So given that they are discrete probability functions, that means that the probabilities sum to 1. So for A, if the probabilities sum to 1, then if we add them all up, including k, we can solve very simply for k that it's 0.2. Now for B, we can do the same sort of thing. We know that these probabilities add to give 1. So given that these all add to give 1, we can set up our equation and solve for k, which is 1/20. Here we have to show that the probability function, that the function is a probability function, and we're given fixed values for x, 0, 1, 2, and 3. So what we're going to have to do is show that the probabilities are first all positive and second sum to 1. So by subbing in 0, 1, 2, and 3 into this function here, we can generate the probabilities here. So 0, 1, 2, and 3. And so our table would consist of 0, 1, 2, and 3, and the probabilities there. Now if we check that first they're all positive, yes, and second they add to 1, and they do. 18, 13, 8, and 3 would give us 42, so they sum to 1. Okay, now this one, in order to solve this, I would draw a tree diagram first. We've got 3 balls selected from 6 blue balls and 4 yellow balls, and they're replaced. That's important because it means that the probabilities stay the same throughout, they don't change. So you can have blue or yellow for the first one. It's been cancelled down to 3/5 and 2/5 from 6 out of 10 and 4 out of 10. Next one could be blue, yellow, and the third then can be blue, yellow, blue, yellow. Here we've got our possible outcomes, blue, 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 yellow, blue, and so on. Now we're looking at probability distribution for the number of blue balls drawn. So there's either 0, 1, 2 or 3. For the first probability, so 0, and now this is this blue path here, that's going to give us yellow, 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 which is 2/5 times 2/5 times 2/5, which gives us 0.064. The highlighted one in yellow is for one blue ball, so we've got blue, yellow, 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 blue, yellow, 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 blue, and they're all 3/5 times 2/5 times 2/5. So we have 3 lots of those, and they add to give us 0.288. Those are our other 2 that you'll get if you work through and calculate them each individually. Now B says the probability that 2 blue balls are chosen given that at least one was blue. So this is the problem we have to set up. The probability that x is equal to 2 given that it's greater than or equal to 1. Now the given that here is the green space here, so I've isolated those 3 probabilities because that's this section here. Oops. That's the section at the bottom there. So the probability that x is greater than or equal to 1 is this part here, and this exact value, x equal to 2, means our answer is 0.432 out of these 3, giving us a final answer of 0.462. Okay, now we're going to look at the expected value, variance and standard deviation next. The first is a measure of central tendency. You've come across these probably before when you've looked at the mean, median and mode when you've been doing statistics. So we're going to be looking at the average mean expected value. Symbols we use for this are mu here and e of x, so capital E of x. Now I want you to think about the dice probability distribution function we looked at originally. We could have outcomes of, if you roll the dice, 1, 2, 3, 4, 5 or 6, and they all have a probability of a 6th. Now if you roll the dice many times and you write down all of those results, you would end up with a number of 1s, a number of 2s, a number of 3s, a number of 4s, a number of 5s, a number of 6s, and over the long haul you would end up with the same number of those. So if you average out those values, average out all those 1s, 2s, 3s, 4s, 5s and 6s, you would get a value of 3.5, and that would be the mean, average or expected value of rolling a dice. So even though you can't actually get 3.5, that's what the expected value is over the long haul. So another way to work this out is to take the value here and multiply by the probability here, and if we sum all of those we will also get to 3.5. Now as the probabilities change, this becomes a much better way of working it out than trying to work out how many we would have over the long haul and then averaging those out. So we're just going to multiply x, which is our value here, by the probability here, and then add them all together. So in this case it would give us 3.5, in other cases we'll get other expected values. And it takes account of the different proportions that these probabilities have. Now, measures of spread include variance and standard deviation, which you may have come across before. The variance is known as var of x. It's used, sigma squared is used to represent that. And the standard deviation, another measure of spread, how far spread out that data is, or those probabilities are. And we use sigma for that. That's lowercase sigma as opposed to the uppercase sigma here. Now, to calculate the variance of x, we find the expectation of x squared and subtract the expectation of x squared. So I'll say that one more time. Take the expectation of x squared, so we're going to have to work out what x squared is up here, and then subtract the expectation of x all squared. The standard deviation is just the square root of the variance. So once you can calculate the variance, standard deviation is pretty easy. Okay. Here's our x's, here's our probability that x equals x. First find the expected value. So write your formula down first. Sigma x times probability that x equals x. So it's 6 times 0.3 plus 7 times 0.3 plus 10 times 0.2 plus 12 times 0.2, which gives us 8.3. So that's the average expected result over the long term. Now, okay, to calculate the variance of x, we're going to need the expectation of x squared. So add an extra row here, x squared, and square each of those numbers. So now we do what we did before, which is multiply x squared by the probability of x, and we add them up, which we do here, and then subtract the expectation of x squared. We previously worked that out to be 8.3, so subtract 8.3 squared, which comes out at 5.4. Now 5.4 then is a measure of how spread out the data is. The standard deviation of x then is just the square root of the variance of x, so it's the square root of 5.4 or 2.3. Okay, so that's it for discrete random variables for now. Thank you very much.